So then first speaker is Sorisano Dorako, and he will give a talk about the STRANGENess in compact star. And you can give a talk in 25 minutes plus 5 minutes discussion. Okay, please.
Thanks a lot. Thank you. Thank you to everybody for having this chance to give this talk with so many friends and unexpected ones also appearing. That I'm so glad. And so this is a chance of reporting on some of the progresses of the last period on the structure of compact stars and how this relates to nuclear and hadronic physics. And so I will summarize the very recent results by NICER about masses and radii of compact stars. And I will first discuss a simple model, which is the model essentially that is being discussed by some of the authors inside the NICER collaboration. And in that scheme, essentially, there is only one type of compact stars, and we will discuss which type of compact stars. And after I will, the second part of the talk, I will discuss other more controversial data, because maybe not everything is already clear, maybe there are still open questions, and if those questions are really open, if really not everything can be...
Przerwie pokazywał wybuch etny, podobno bardzo interesujący. Ale...
Yeah, a voice, I don't know, somebody is speaking maybe. So if not everything is already clear, in the sense that if there are more data than the ones used in the simple model, then I will discuss an alternative explanation that we have been developing during many years with also some of the people that are present today, I mean, from Isaac to Ignazio, and okay, also people that are not present, of course, Giuseppe, etc. So let me first of all summarize the new result by NICER. So these new results are based on a new technique to measure masses and radii of compact stars. This new technique is based on, I mean, you study objects which are rapidly rotating and they have a hotspot. And apparently there are quite a few compact stars rapidly rotating and with a hotspot. The hotspot can be generated, for instance, by the presence of a strong magnetic field that after is driving matter to fall onto the specific area of the surface of a star, making it hotter. And so this technique is based on two ideas. The first idea, rather simple, is a Doppler effect, in the sense that if this hotspot is on the surface and the star is rapidly rotating, then of course when the hotspot is rotating towards you, you get a Doppler shift towards the blue, what's called. And when the hotspot is rotating away from you, you get a red shift. So you get a Doppler widening of the signal, and at the same time you have modification of the time structure of the signal, because if the hotspot is on the wrong side, meaning is not facing you, then in Newtonian mechanics you would not collect any of the photons emitted by the hotspot, but in GR, in general relativity, due to the very strong curvature, you still detect some of the photons, even if they're coming from the wrong side. So this is what you expect to see, let's say, in GR concerning the flux, depending on the position of the hotspot. And this is what you expect in Newtonian theory. And this last correction depends on the compactness, while the Doppler effect essentially depends on the velocity. And since you know the frequency of rotation, then you can estimate the radius. So it's a very nice and way of measuring masses and radii. So these are the main results that have been obtained. I mean, this technique has now been used twice. a couple of years ago on this object here, and very, very recently, I mean, literally a few days ago, on this other object. And they will discuss the implications of this result. The first thing that anyway one can immediately notice is that, okay, the first object had a mass typical of neutron stars, about 1.3, 1.4 solar masses. The second object is one of the very massive neutron stars. And in both cases, the radii are large. So one can, already just looking at the number, one can conclude that probably there is not a strong softening of the equational state when going to large masses. What is instead was expected in certain schemes, theoretical schemes. Okay, one can also put together, of course, the data from LIGO Virgo obtained from studying this event, the event of August 17, the merger of two neutron stars. And the data are not very constraining in the sense that you obtain some limit on the radius from measuring the so-called tidal deformability. What I mean is that you measure, but for sure, the shear mass, and the shear mass is a combination of the two masses of the two objects. The shear mass is somehow related to the total mass. After they can get an estimate of the ratio of M1 and M2. And finally, they can also estimate the so-called tidal deformability. At that point, you can make a plot like this of the density of probability of the tidal deformability. And you can see that the analysis came out with a double peak structure. One peak was corresponding to very low values of the tidal deformability. Very low value of tidal deformability in a simple scheme, at least, can be associated with very small radii. Here there are examples of equational state independent of their physical relevance or not, but as you can see, if you have a tidal deformability of this order, the radius should be of the order of, let's say, 11 kilometers or even less. And instead, the second peak here is about 12 kilometers. Notice that anyway, the first peak is quite significantly larger than the second peak, but this is what it is, nothing more than this. So you can put together the information coming from NICER 1, NICER 2, and the LIGO Virgo analysis of that event. Other events, honestly, they don't provide serious constraints. I mean, other events in gravitational waves. And you come to this rather simple model. The model is telling you, okay, this here are two different analyses of the same object made now by NICER. There are two groups that came out with slightly different results. Notice anyway that the results are overlapping in this area, which is between roughly 12 and 13 kilometers, or even a little more than 13 kilometers. This is not, it's a different analysis coming from X-ray emission of an object. Is not something, this object here, but it's totally compatible with this. These curves here are roughly what you get from the analysis of gravitational waves of the event of August 17. And this very large area here is the analysis of the first object studied by NICER, so it's not very constraining. So the most constraining results are probably these ones, and you have a way to incorporate somehow also what you get from gravitational waves. So you can see that if you want to explain all this data, you can, and you can use some equational state which are relatively stiff. In particular, let's say, for instance, this MPA or ALF or AP3, let's say. I will discuss later on about the core stars, but for a moment, concentrate, for instance, on MPA and AP3. They are both equational state only made of neutrons, protons, and electrons. And MPA is Mütter, Prakash, and I forgot the third guy, is Dirac-Bruckner Trifort calculation, and AP3 is a Mark-Van-der-Lipan, is a non-relativistic calculation. Fine. So, how can you reach this conclusion that for this simple model? How can you, so to say, introduce this simple model? This is what has been done in particular by the analysis of Miller. This is one of the two papers of the group of Neisser that appeared. And let's have a look a moment which are their hypotheses. In particular, they consider, so to say, that we know the structure of a neutron star from theory, so to say, but only up to about 0.5 rho 0, which is, of course, a rather low density, not even up to rho 0. So at that point, from 0.5 rho 0, they essentially assume that the gravitational state can be whatever. And from that sort of Bayesian analysis, they come with final results concerning the radii of compass stars for these two masses. So as I said, rather large radii, and from this analysis, they are also rather well constrained. And these are three representative equational states that I discussed before, satisfying somehow the limit of Neisser, analyzed by Miller. So that's the end of the story, but not really. In the sense that, I mean, as usual, I borrowed one slide from Isaac and another slide from Ignazio, because I like that. And so if the density at the center of a compass star exceeds something of the order of 2-3 times rho 0, then we know that hyperons will be produced. It's not, so to say, a strange hypothesis. It's a matter of fact. It's just based on quantum mechanics and statistical physics, no more than that. To deny that means to deny quantum mechanics statistical physics. So, okay, hyperons will be produced. Is this a disaster? No, not really, but we have to take into account of that, okay? I mean, so let's look in particular, are we exceeding 2-3 times rho 0 or not? So let's consider these three equational states that are somehow spanning completely the area indicated by the analysis of Miller. And we can see, for instance, let's have a look again, sorry, here. The AP3 is the one with the smaller radii, therefore the one where the highest densities are reached, while MPA1 is a larger radii, therefore smaller densities, a given smaller density for this ALF3, but ALF2, sorry, that is a little bit strange object, and we'll not discuss too much at that point, but I'll come back a moment. So if you take these two objects, for instance, you can see that this densities I was speaking about, twice rho 0, 3 times rho 0, are reached for masses which are very moderate. I mean, of the order between 1 and maybe 1.5, 1.6 other masses. So somewhere in between is totally unavoidable that you start producing hyperons. And let's go back because I said I don't want to discuss too much ALF2 because actually it doesn't correspond to a real equational state. It's a parametrization of an equational state containing quark matter. But the parametrization, if you really look at it, is completely different from the original equational state. So it's mysterious how this ALF2 is systematically quoted because it corresponds strictly saying to nothing. It's not an equational state. It's a not totally satisfying some parametrization of an equational state. So strange object. So let's instead go to something that is more concrete. For instance, this calculation by the Norwegian group, quite old. And as you see, this is an example of equational state that instead is very stiff. And so you get very large radii. So you are really touching the limits of the analysis of Miller. But still, even in that case, this 2-3 times rho 0 at which you expect hyperons to be produced is reached at least for the most massive neutron stars. So again, is this a disaster? No, because it is possible to use nuclear physics and hadronic physics to the best of our knowledge and still satisfy those limits. I just present one example because instead I would definitively violate the time limits of this very recent calculation by this group. They published many calculations on this idea. And essentially what they incorporate delta resonances, hyperons, and even count condensation. And of course, as you can see from this figure, they start producing the hyperons exactly the density that one was expecting, between 2 and 3 times rho0. Where slightly larger densities if the delta particles are also produced, but still you are there. This is unavoidable. It's not something that one can like or not like. I mean, to decide if you like quantum mechanics, statistical physics, not anything else. And they also consider the possibility of having kaon condensation. And as you can see in the next slide, they get equational state which are very interesting because, first of all, they reach roughly twice two solar masses, not much more than that. Okay, they can reach about 2 solar masses. And the radii they are obtaining are really sitting in the right area. The radii are really between 12 and 13 kilometers. So this, I think, is a good example. An example, not the only one, of course, I mean, but an example that is possible to satisfy at least some of the constraints existing, introducing all what we know of nuclear and hadronic physics, and this is a possible solution, okay? After, is this the solution? It does not depend on theoreticians, but on nature. And in particular, it will depend on the question, are all the data being already discussed or there are other data? So before going to the second possibility, let me just stress that, of course, the solution, a solution like this one, strongly depends on nuclear hadronic physics. It depends on the value of the symmetry energy at about twice rho0, on the value of the delta nuclear potential, of the gamma optical potential, of the hyperon nuclear potential, of the hyperon-hyperon interaction, of the presence of the sigma star meson, etc. So that solution is really strictly linked to all what we can obtain from the lab concerning hyperons, deltas, kaons, and so on and so forth. So is this the end of the story? Maybe yes, maybe not. I mean, what I would not like is that somebody tries to jump on the wagon and start screaming solution, solution, because I honestly think that we are still very far from that. Okay, let's skip. So what, for instance, seems to indicate that maybe not everything has already been understood. First point, in this paper of last year, they also discussed the analysis, I mean, of this object here. And they obtained a completely different results. They obtained a radii of the order of 11 kilometers, with an error bar that you can read from here. So essentially, almost completely outside of the result obtained by some analysis by NICE. So what's the difference? I think that, okay, there is one difference, but probably it's not enormous. First of all, they think that we know about nuclear physics, not just up to 0.5 rho0, but let's say about 1 to twice rho0. There is some difference if you accept that, but the main difference is that they decided to reject all solutions, so to say, having a maximum mass larger than about 2.3 solar masses. This was due to phenomenology, okay, and but I will discuss in a moment. There is probably something more than phenomenology, okay. And so this essentially is what they have used. They studied this object here, and they cut at 2.3 solar masses. All the equational state violating going above 2.3 solar masses were rejected. They came out with the conclusion that the radius was significantly smaller than what described by NICE. Of course, the idea of radii significantly smaller is not exactly new, and it was discussed analyzing X-ray spectra in this paper, in this paper, in this paper, etc., etc. So all these papers are essentially suggesting radii which are outside the range indicated now by NICE. Of course, all these analyses are, so to say, affected by being model-dependent analysis. They can depend, for instance, on the atmosphere. But in some of the cases, they discuss it quite at length, the effect of the atmosphere. So I would say that is at least an open question. Let's go back to another point that I was mentioning, which is the maximum mass of a neutron star. So recall that this analysis here, this result here was probably based on the idea that by truncated at 2.3 solar masses, they were saying we don't want to have more massive objects. They did this from phenomenological reasons associated with the kilonova produced in association with this or blah. But there is also another point. The other point is that if instead you have an object of 2.5, 2.6 solar mass, which is not a black hole, it's a compact star, then you have some strong tension with nuclear physics. This has been discussed in a few papers, and you have a strong tension with nuclear physics, and you have also a strong tension with having relatively small radii below 12 kilometers. So this is a potential problem in the sense that if there is an evidence of objects like this, then how do you describe? You apparently are not really able to describe in terms of normal nuclear matter. Instead, you're violating some of the constraints, some of what is known concerning nuclear matter. So the first problem that I was mentioning was the radius that I mentioned here and here. The second problem is maybe there are objects which are very massive, and then it's not clear how to describe them in terms of nuclear physics. And let me mention a third problem with this paper in preparation, but actually, I mean, this result that I'm discussing here, that, okay, we would hopefully publish, but is essentially already contained in a sense in the analysis that I presented here. So we are quite convinced that we are just updating this analysis with the new data. And which is the problem discussed here? The problem is very simple, that if you have a neutron star black hole merger, you can estimate the amount of mass ejected. And it depends, the amount of mass ejected, therefore the strength of the kilonova signal, it depends on the equation of state. Now, if you take the three equations of state that are satisfying nicer result, you expect a lot of mass ejected and you expect a strong kilonova signal. In the alternative explanation that I'm going to discuss in a second, you don't expect such a strong amount of mass ejected, and so you expect a very weak and maybe unobservable kilonova signal. Point is, up to now, there is absolutely no evidence of a kilonova associated with a neutron star black hole. Okay, so which is the alternative explanation? I mean, which is another other possibility? Is that there can be objects made essentially entirely of quarks. And this explanation is based on the fact that pure quark matter phase is very stiff, and is based on the idea of having satisfying the Witten hypothesis about absolute stability of strange quark matter. And okay, we started developing this idea with Ignazio, I think something like 15 years ago. At that time, there were no strong indication of very massive stars. So at that time, we had a slightly different idea about how to position, so to say, the hadronic stars and the quark stars. But now if you incorporate the fact that, I mean, you need to reach a certain large masses and maybe relatively large radii, and if you want to try to explain the small radii, then you have to have this sort of configuration. The idea is you have hadronic stars made of neutron protons delta resonances, neutron protons delta resonant hyperons, and you don't reach with these normal neutron stars with two solar masses, but you can have small radii. But you can also have at the same time strange quark stars, and strange quark stars can reach very large masses, but with large radii. And after there are a lot of subtleties that I don't have time to discuss concerning the transition from year to year. Okay, we studied in plenty of papers, this thing. And let me just mention one thing that is very tempting. Is there absolutely no evidence of a bimodality? I mean, that there are two families of compact stars. Well, let me just mention one. There is maybe a little more than that, but one thing, that if you study the distribution of the masses of compact stars, there is a quite strong evidence that is bimodal. And funny enough, the first Gaussian, so to say, if you want to model in terms of two Gaussians, is spanning essentially exactly the region that we would call neutron stars, And the second one is spanning the region that we would call quark stars. Okay, so this is very tempting, associating explicit objects with ether, neutron stars, or quark stars. This is a paper we published now this year, essentially, and it shows what? That within this explanation, I mean, you can have significantly more compact objects which are made of hadrons and more stiff objects made of quarks. We can explain the possibility of reaching 2.5 solar masses. This would be, so to say, our quark star that arrive to 2.5 solar masses. And the soft objects, the objects with small radii will be hadronic stars. Let me just mention one thing, that if we use the data for the objects having a mass larger than about 1.45 solar masses, the data available, we have also done our Bayesian analysis, but using a STRAngeness star. Without incorporating the very last result of NICER, you get these red curves, and you can see where NICER results are sitting. I mean, this is just how it is. I don't want to comment more, okay? So this essentially is the last slide, and the future is very promising, because there are, I don't have time to discuss this, but there are many ways of testing this alternative model, and of course, we test the simple model, so to say. In particular, you can hope that a new measurement of radii by NICER, maybe by EXTP, or equivalently, measures of the moment of inertia are maybe providing or negating the existence of two families of compact stars. And after, you have plenty of phenomenological implications that I don't have time. Let me just, and this is really the last slide, I think, yeah. Let me just mention that if you study this type of scenario in which you have at the same time hadronic stars and STRAngeness stars, so you are satisfying with an hypothesis, then the phenomenology is incredibly rich. And that also means that your scenario can be killed in principle by plenty of observations. And here I just made a short list, but there is something that in the last few years I really became more and more interested in, and is the possibility that dark matter is composed of strange core matter. This was already discussed in the original paper by Ed Whitten in 1984, and I think it is an open question, an interesting one. So, okay, thanks a lot for this.
So thank you very much for your nice talk. And now in the paper is open for the discussion. Okay. Any other question or comment? Okay, Peter Kovacs, please.
Yes, thank you. Do you hear me?
Yes, thanks.
Okay, Drago, I would like to ask, maybe I have two questions. One of them is that how much you can reduce the error on the radius. So what can you achieve? That's
yeah, NICER is claiming that they are collecting again data. So essentially, I think that in the case of NICER, this is definitely possible, because at the very end, their analysis is really based on the errors, in the sense that if you go back to their technique here, it is clear that in order to extract, for instance, the value of the compactness, you have to compare these two types of curves. And if you have better data, you can increase the precision, can reduce the error. Of course, another possibility is to measure the same thing for other objects, or to do something completely different. For instance, to measure the moment of inertia with radio telescopes. But if you want to stick with NICER, they can. They claim that we are going to do. They will keep observing the same object, so it's possible. Yeah. Okay.
And my other question is related to this, that you said that the hyperons start to show up around 2-3 row 0. But so maybe this is a note that this can happen, that based on effective model investigations, that at 3 row 0, then you are already in the deconfined phase. What do you think about that?
Yeah, absolutely. I mean, that of course is another possibility. What I think is not really possible is that you can reach densities significantly larger than 3 times ρ0, and you still have only neutron protons and electrons. That I think is not very much plausible, because essentially, as we know, the moment in which you pass is 2-3 times ρ0, you have essentially two possibilities: or you start producing resonances and hyperons, or you deconfine. The problem with the confinement is that if you really deconfine at relatively low densities, then the type of solution that you would get is most likely the solution in which you produce a hybrid star, and that would essentially imply that you go to smaller radii for larger masses. And that now seems a little bit difficult to reconcile with the fact that at 2 solar masses, the radii are between 12 and 13 kilometers. But I think that one has to be very careful in driving conclusions now. We have to wait and be patient and see what nature is telling us.
Okay, thank you very much.
Thank you.
Okay, next, Andres.
Okay, thank you very much, Alessandro. Very nice talk.
Ciao,
Nice to see you.
Anders.
Ciao,
Nice
ciao.
to see you. Ciao.
I just have a very simple question. You talk about these strange matter type of stars that they have higher radii with the same mass, let's say. So that means that they are less dense in a way, probably because they have a stiffer equation of state, and you cannot press them so much. So
there is a subtle thing. You don't really need to have an ultra stiff equation of state for quark matter, because there is a little trick that was already discussed in the paper in 1986 by Pavel Hensel. And the point is that if you study strange quark stars based on the Witten hypothesis, you can compute the adiabatic index. The adiabatic index is the derivative of the log of p respect to log of rho. So therefore, you have in front of it, you have a rho over p. Okay. Now, what's the point? That if Witten hypothesis is correct, you have a zero, the pressure at finite density. So the adiabatic index is essentially diverging at the surface of the star, strongly stabilizing the star. And that essentially implies that you can have even very massive configurations without the need of having a violation, for instance, of the conformal limit for the speed of sound. Okay,
but then what is more or less the central density of these objects?
The central density is of the order of, let's say, 1.5 twice ρ0. So you go from very large densities. So here you can easily reach densities of the order of
5. Yeah.
Yeah, exact. And after, exactly because of what you were telling, the density somehow diminishes. We studied this problem for years and years because nobody was convinced that what we were telling was correct. But I think that maybe now we convince people is possible. Is definitively not a detonation, is a deflagration, and is strongly exothermic. And why is possible to have this transition? Essentially because if Witten hypothesis is correct, the strong interaction plays a role which is even more relevant than gravity. So you pay to gravity the increase in the radius, but you gain a lot from the strong interaction, and you can show numerically, quantitatively, that this can be sufficient to make this process possible.
Okay, thank you. I enjoyed your talk very much.
To see you, so nice.
Okay, bye-bye, thank you.
Last question is Ignacio Bompaci.
Okay. Alessandro, concerning the analysis of the data for J0740, there are two analyses, the one of Miller and the one of Rayleigh. In a few words, do you remember, you can tell us what is the difference in this analysis?
Oh, I mean, you mean between these two results? Oh, gosh, I think that they assumed, as usual, something slightly different concerning the atmosphere, if I'm not mistaken.
The atmosphere, okay.
I'm not 100% sure. I'm sorry for that.
No, okay, okay, that's
because I
fine.
think that Miller discusses at the end of the paper why the result is slightly different. If I am not mistaken, one of the reasons is as usual atmosphere, but I cannot completely bet on that. I'm sorry, I forgot.
No, no, okay, okay. I tried to read the two papers are so sometimes so technical, so I was not able to get this point.
Yeah,
So,
I think it was something
thank
like
you.
that. I can recall
Okay.
it wrong. It's possible to recall it wrong.
Okay, so thank you very much for the nice talk. Okay, let's move on the next speaker. Okay. Could you answer? Okay, so next speaker is Dr. Isaac Bidana. Okay, could you share the screen? Okay.
So can you see?
Yes.
Okay.
Yes.
So,
Okay, so he will give a talk about transport coefficients of the hyperonic neutron star cores. Okay, please.
okay. So first of all, I would like to thank Christian, Catalina, and the rest of the organizers for the invitation. It's always a pleasure to participate in this series of meetings, even if this time is unfortunately online. So as Emik already mentioned, so what I basically will present here is a preliminary result, some preliminary results of a recent study on the transport coefficients of hyperons in neutron stars. And this is a work which has been done in collaboration with Peter Sternin from the Joffe Institute in St. Petersburg. So let me start with a bit of motivation. I mean, all of you know that, I mean, that the history of hyperons in neutron stars is already very long. So that's back on time, almost 60 years since the initial work from Barsuyan and Sakayan. And many people have basically studied the role of hyperons. But the majority of the work that are in the literature, not to say almost all of them, has basically concentrated on the role of hyperons on the equation of state, the composition, and of course on the mass. And as you know, there has been a lot of activity in the last years on trying to solve the so-called hyperon puzzle, which is basically a problem which tells that, okay, if you have hyperons in a star, which is something energetically unavoidable, then the equation of state becomes solved, and as a consequence, the mass, and in particular the maximum value of the mass, is reduced. And it's reduced to values which are basically incompatible with the recent observation, in particular with these two solar mass objects. However, the point is that neutron stars are not static objects, they are evolving objects, and in fact, there are different dynamical processes that can happen. And to have a reliable theoretical description of these processes, one needs, in addition to the equation of state and the composition of masses, you have to know also all the properties, in particular the transport properties. So in this work, basically, we'll concentrate on, okay, I mentioned here two, but there will be a third one, on the thermal conductivity and the shear viscosity of neutron star with hyperons. So just to show you why these quantities are important, what you have here is just a schematic plot of the neutron star cooling curve. So this is temperature and surface temperature versus time for two typical scenarios, the so-called fast cooling scenario and the slow cooling scenario, where you can distinguish generally three epochs. So the first one, which is relatively fast, is the so-called correlation time or epoch. The longest period is dominated by neutrino emission, and then you have the last type, which is basically dominated by the photon cooling emission. And to obtain this kind of course and compare with observation, one essentially have to solve that heat equation, and there are different ingredients. In particular, you need luminosities from photons, neutrinos, some heating mechanisms, but you need also the thermal conductivity and the head capacities of matter. And this, of course, depends on the composition of the star. There are other kind of dynamical scenarios or processes that are important. And for instance, neutron star can oscillate, can present modes of oscillation, which can be dampened by different viscous mechanisms. In particular, one of the important ones are the so-called R modes or rotational modes. This is a oscillation mode with the Coriolis force as a restoring force. And this mode, when it becomes unstable, it can lead to the emission of gravitational wave in hot and young neutron stars. So what you have in this plot basically is this continuous line is the critical frequency or the maximum frequency that a neutron star can reach due to the existence of this modes, which makes the star unstable. So the region in between, so when the star is rotating with a frequency larger than this critical value, what happens essentially that this mode is unstable and it leads to the emission of gravitational wave. If the frequency is below this limit, then the mode is basically damped by different viscous mechanism, in particular for higher temperatures or for the beginning of the history of the star when it is young. The main dissipation mechanism is due to bulk viscosities at longer times, so when the star is already quite above and much cooler. That is the shear viscosity that takes care of the damping. So let me just summarize, just in case I will not be able to finish it all. This is a spoil of what I will basically present. So as I already mentioned, we have studied transport properties, in particular, as already mentioned, thermal conductivity, shear viscosity, and the momentum transfer rates, which are important for the magnetic field evolution of neutron stars. And this has been done for non-superfluid matter. This is important, so we have not included superfluidity, of a mixture of neutron, protons, sigmas, lambdas, and of course leptons in beta equilibrium. And as I will show, you need some macroscopic input for the question of state, and this has been obtained from a non-relativistic Brunner-Hartree-Fock approach, in which we have used for the nucleon-nucleon pair of interaction, the well-known argon-18 potential supplemented with a three-body neutron force. And the hyperonic pair is described in the hyperonic nucleon and hyperon sector by the old Megan 97 version E model. So what we have basically find is that the neutrons will, as you will see, dominate the baryonic contribution to both transport properties. And this is exactly the same that happens when you consider a neutron star with only nucleons. And we have also found that, at least in the case of the thermal conductivity, also the total thermal conductivity, so the baryon contribution plus the electron contribution, is also dominated by neutrons over the whole range of densities. The contribution from the other baryons are small, as you will see, but still they are important because basically they mediate the neutron mean free path. And something that is in fact different from what happens in a situation in which you only have nucleons is that because of the electronization of the star that happens as soon as you start to produce sigma minus, the neutrons also dominate in this case the total shear viscosity at higher densities. And this is contrary to what is found in the case without nuclear hyperons, because in that case the leptons dominate over the whole range of densities, this transport coefficient. Okay, and this is Peter. Yes, so let me start with. Sorry. No, sorry, somebody was entering in my room. So the calculation of the transport coefficient basically is based on the transport theory of a multi-component Fermi liquid. So the starting point is the Landau kinetic equation, where you have on the left-hand side all the driving terms involving the temporal derivative and the gradients with respect to coordinates and momentum of the momentum distribution functions of the different quasi-particles and the single particle energies of the quasi-particles. And on the right-hand side, you have the Boltzmann collision integral, which looks in the usual way. And the more important piece here is the transition probability, which is essentially described via the T matrix. In this case, will be of course an medium tree matrix. The scattering of a quasi-particle I with a particle J with momenta P1, P2 into a final state of particles KL with momenta P3 and P4. Of course, this is a complicated equation to be solved numerically, and the usual procedure is to linearize the collision term. And essentially, the idea is to consider some small perturbation of the momentum distribution function. So you write the momentum distribution function for a given quasi-particle of a given momenta simply as the equilibrium distribution function. Of course, the Fermi-Dirac if you consider fermions, or Bose-Einstein for the case of boson, or the mass with Boltzmann you consider a classical gas. And then you have a first linear term which contains essentially the derivative with respect to the energy of the equilibrium momentum distribution, is linear on the temperature, and then this function phi, which basically is characterizing the deviation of the momentum distribution due to a given perturbation. And of course, this depends on the type of perturbation you consider. So when you do this, the Boltzmann collision integral looks like that. And in addition, this is still complicated to solve. It's a rather numerical cumbersome problem, but we are working on a dynamic limit. And in this case, essentially for the Boltzmann equation can be written in a very compact way, where you have the linear collision, the Boltzmann collision term, some driving term, and then the derivative of the equilibrium momentum distribution with respect to this variable x, which is nothing else by just the energy referred to the chemical potential and then divided by the temperature. So this driving term of the Boltzmann equation, essentially for any kind of transport problem, can be written in can be factorized essentially as a product of different pieces. The first this F is just a scalar function which depends on the Fermi velocities, the temperature, and then contains also all the effective masses and all the possible numerical coefficients. This function xq is a function that in general depends only on the variable energy. So this small x, which is just, as I showed you before, is just this difference with of the energy with respect to the chemical potentials. dq is in general an irreducible tensor quantity. For instance, you can imagine some spherical harmonic or whatever. And q's contains essentially all the gradients of the different variables which specify the local equilibrium of the system. So for the particular case of the thermal conductivity, this is how the driving term looks like. But you have basically the gradient of the temperature, and then here is a prefactor which depends on the velocities and the temperatures. And for the shear viscosity, what you have here is basically the derivative from the y direction of the x component of the fluid. So then, of course, when in order to solve, what is usually done is you assume some form for these functions, and in fact, you assume something similar to the form of the driving term, where you have some function of the energy, some irreducible operators, and some gradients. And then once you solve the question for the phase, you can obtain the transport coefficients basically as a linear combinations of these functions. And this is the general expression for one of these transport coefficients. So basically, you are summing over all the passive quasi-particles of your system, or all the momenta that these quasi-particles can obtain. And what you sum is essentially a combination of this function, which again have the same similar structure as the fifth function and the driving terms, and then you have the fifth functions. So that is, let's say, in general. So in a particular case for the thermal conductivity, the shear viscosity on the momentum transfer rates, which it looks like that. Essentially, you have some these numerical prefactors and temperature dependence. And then all the information from the transport is contained in this lambda function, which are nothing else than the mean free path of the different species. And the important thing is that, okay, the mean free path, they are for the thermal conductivity, shear viscosity on the momentum transfer are in general different. And they depend, in fact, on the particular problem you are going to solve. And they have to be obtained microscopically. So in practice, what you have to do, what we have done is once you have linearized the system, at the end of the day, you get a system of linear equation for the mean free path, which typically look like that, where the main ingredient or microscopic ingredient is the transport matrix, which basically contains the scattering in medium transport cross sections. So there is an additional simplification is that, well, as you will see, okay, in our system, we have baryons and leptons, and some of the baryons in addition have charge. So you have scattering, which are mediated by the strong interaction, and scattering, which is mediated by the electromagnetic one. So in the case of the neutron star cores, because the off-diagonal pieces of these matrix elements involving, the mixture of these matrix elements coming from strong interaction and electromagnetic ones are small, and essentially one can decouple, so you have basically two subsystems. Okay, and this is what you have for the momentum rate. So for the case of the transition cross section mediated by the strong interaction, this how they look like for the three transport problems for the thermal conductivity, the shear viscosity, and the momentum distribution. You have some effective masses, the typical T² dependence, and this is because it's a typical Fermi liquid behavior for the baryons. And the main ingredient here is these are angular average of essentially the in medium cross sections and some additional factors. So all the macroscopic input enters basically in the calculation of this of the medium scattering matrices, which in our case, as I already mentioned at the beginning, are obtained from a Bruckner-Halfrey-Fock calculation. That is for the transport part coming from or mediated by the strong interaction. They, of course, as I already said, some transport contribution coming from the interactions, from the electromagnetic interaction, which of course involving the two leptons and the protons and the sigma minus. And the main difference is essentially between the transport amplitudes originated or based from the strong interaction and the electromagnetic one is that the last ones, so the electromagnetic ones, they do not follow the typical Fermi liquid temperature dependence. So essentially, they do not scale as T², and essentially they have a weaker dependence. So, for instance, just to show you, in the case of the thermal conductivity, this is a very simple expression. So in fact, they do not depend on the particle content, and is linear on T. So the rest of the terms is finite structure constant, and this is the zeta function and so on. For the shear viscosity, it is a bit more complicated, and in fact, it's the sum of two contributions. There's a transfer contribution, which is give transport matrices proportional to T to the 5/3, and some longitudinal terms, which are in this case proportional to T squared. So, in addition, once one look into the matrix elements, so the off-diagonal matrix elements, let's say involving leptons and baryons, are small, and in a good approximation, one can also simply separate this contribution and keep all the diagonal terms. So let me already start to move to some results. So let me mention a bit of the microscopic input. So the microscopic input, as I already mentioned, is basically the scattering, medium scattering, the matrices between all the different species, and of course this has to be done on conditions of beta stability. So, and in addition, you need also the effective masses. So the microscopic approach that has been employed is the Plug-Nahatefok approach of hyperonic matters, as I already mentioned, using the argon 18 with Urbana-9 and the 9-97E models. So you start by solving the Berthel-Gosson equation self-consistently with the single particle energies of the different species. On top of this, you impose equilibrium with respect to the weak interaction processes and charge neutrality. And once you have a solution, at the end of the day, you basically simply evaluate the effective masses from the corresponding derivative of the spectra, and the G matrices are taken at the corresponding Fermi surfaces of the different species. So what you have here is the composition that is obtained for this particular model, and this is all the effective masses evaluated at the corresponding Fermi momenta of the different species look like. So let me already move to the transport coefficient. So now imagine for a moment, and this is essentially what happens, that the non-diagonal elements of the transport matrix are small. If this is the case, then your system of equations basically becomes diagonal, and the mean free path is basically given by the inverse of the diagonal matrix elements of the transport matrices. And this is what is shown here as a function of the density for the case of the thermal conductivity and the shear viscosity. So what is in fact shown here is a T-independent combination. You have the matrix element multiplied by the power to the -2 of the temperature in units of 10 to the 8 kelvins, and in the end it's taking the logarithm. So for this case, it has the baryonic contribution, so from neutrons, protons, lambdas, and sigmas. So the first thing you'd see is that if you just look into all these matrix elements look like for the case of thermal conductivity and shear viscosity, they look very similar. The form, the shape, or the behavior you want as a function of the density for both the coefficients. And then you also notice that the neutrons ones as the one which predict a lowest value for the transport diagonal matrix elements, which means that they will in fact give the largest mean free path of all the possible species. And that implies that neutrons will dominate the transport. And in fact, as you will see, because remember that the coefficients are essentially proportional to the mean free path. So the largest contribution to both coefficients, to the shear viscosity and thermal conductivity, at least on the baryon sector, will be dominated by neutrons. So we already know simply by looking at these matrix elements. In the case of protons and sigmas, if you look into the matrix elements, they are basically 1 to 2 orders of magnitude, much larger. So essentially they scatter more effectively. And for densities larger than the typical 0.5, they essentially go on top of each other. But this is simply because the composition is telling you that you are basically the same number of protons and sigma minus, because you have almost a complete electronization of the system. And well, since the matrix elements are much larger, that will mean that the free path will be smaller. And in fact, we don't expect protons and sigmas minus to give too much contribution to the transport coefficients. For the case of the lambdas, they lie on between, and they will give some contribution, but of course only from the density, from the onset density of the lambdas to the system. So let me show you that's as for the diagonal matrix element, but one can have a look to the off-diagonal ones. So essentially these are the same quantities. Well, there are two types of lines here. The solid lines is just the ratio of the off-diagonal terms, matrix elements with respect to the diagonal ones. The dashed ones are just the off-diagonal ones. for the case of thermal conductivity and shear viscosity. So if you just, okay, this is a bit messy picture, but if you just concentrate on protons and sigma minus, and you look into the solid lines, what you notice immediately is that as soon as you have sigmas, the collisions of between protons and sigma minus, you see here, become the dominant ones of these two species. So these two species basically collide mostly between them and much less between the others. And in addition, these transport matrix elements are large. So that, as I already mentioned, that will mean that that they will contribute very, very low to the transport, but still they will influence, of course, the transport of the other species, because of course these matrix elements are not zero. So I have just 3 more transparencies showing you finally the results. So this is the thermal conductivity for 3 different temperatures, from 10 to the 7 kelvins up to 10 to the 9 kelvins. And as I already mentioned, so okay, the continuous more solid line is the total thermal conductivity, adding all the contribution from baryons and leptons. And what you can see immediately, especially for the lowest temperature and 10 to the 8, that the neutrons dominate. First, they dominate the contribution of all the baryons, but they also dominate almost the total value of the thermal conductivity, except for the largest temperature, where the electron contribution is also relatively large, especially at lower densities and okay, well, also high densities. So, okay, let me show you now the shear viscosity. So in this case, again, so it's the same for the same 3 different temperatures. And as you see here is that the leptons, in particular electrons, dominate the shear viscosity in the low density region. And this is, and then this transport coefficient is dominated by the neutron one. This is something that I already mentioned, is in contrast to what you find, and unfortunately I don't have here the plot, but if you are interested, you can go to this reference and look into this figure. When you have only nucleons and leptons, electrons dominate the shear viscosity over all the whole range of densities. So that is one of the main differences with respect to a case in which you don't have hadrons. And so finally, that is the momentum transfer rate. As I mentioned, this quantity, this is a transport coefficient that is important if you are interested in studying the magnetic field evolution of a neutron stars. And I want only to mention that if you look into the contribution from proton and sigma minus, you immediately notice that this is the largest one, but you have to take this number with a bit of caution, because in particular, as I mentioned, we are using this Megan 97E model, which predicts strong attraction in this channel. So this can be simply a consequence of the model we are employing. So I'm almost finished. So I go back to essentially the same transparency that I already showed, that is the main conclusions. And I want just to finish by thanking you, and again, the organizers, and Force Peter for his help in this work. So thank you very much.
Thank you very much for the nice talk, Isaac. So now paper is open for the discussion. Okay. Any question? Okay. So Ignacio, you have a question? Or not? Just only you hang a hand? Maybe not. Okay. So if so, next is Albert.
Yeah.
Okay.
Thank you, Isaac, for this nice talk. But I have probably a naive question, but I wonder why you consider the mean free path as different magnitudes depending on the thermal theater you study.
No, sorry, can you repeat? No, because it's like that. No, it's not that I don't. So the mean free path basically depends. Sorry, let me. Okay. So these are the transport coefficients, and all of them depend on the mean free path. But the mean free path is different depending on the problem. In fact, this is what you can see here. So this is how they look like. Look, so these are okay. The mean free path essentially are given by this linear combination of the transport cross sections. But the transport cross sections, you see, they are not the same for thermal conductivity and shear viscosities. I mean, look, okay, you have, let's say, the matrix element is the same, so this is the same, but the prefactors, you see, it's not the same.
Yeah.
And also these quantities will depend on the Fermi momenta. So in general, they are different. So the G matrix is the same because it's the input, and this is what is giving you this Q that then you average here. But the rest of the coefficients of the time are different. So in the end, you have a mean free path which is different depending on the transport coefficient that you are interested in.
Okay, thank you.
I mean, this is coming from the general theory. So you start from here and then you start to derive. Basically, you have the different terms, and at the end of the day, you get this. So you get that they have some functions which are not the same, and this, in the end of the day, are entering in the cross section. So that's all.
Okay.
But the in medium G matrix is the same. It is the same. So this G, which produces Q, is just the other factors that are different depending on the transport problem.
Yeah.
I don't know if this is answering your question. But,
Yes. Thank you, Isaac. Thank you.
Okay, next in Constantine.
Yeah, thank you very much for the nice talk. So my question is, you mentioned the different temperature scaling for lepton and baryon contributions to the transport coefficients, right? So yes. What is the reason for that?
Well, honestly, I mean, I'm not really an expert on transport, so I cannot really, I don't know.
So normally we just consider the baryon Fermi liquid and the lepton Fermi liquid, and somehow we get something non-Fermi liquid. This is interesting, I think. Yeah, thank you. So if I may, second question is about the result for the viscosities you have shown. So, and what I have noticed is that probably at least at large densities, the next by the order of magnitude contribution is from lambdas, right? So
yeah,
yes. Yeah. So what would happen if the model was working this way, that lambdas appear earlier and accumulate in larger amounts? So
well, probably they will contribute that. I suppose they will give a larger contribution at lower densities. Probably. I don't know if they will dominate. That will depend. Of course, this is model dependent. But for sure they will give a larger contribution. I mean, let's assume that basically you have the same time of tendency, but starting at lower density. So really you will have a larger contribution. Yeah, sure, they will contribute more. But of course, this is also affecting the rest of the composition. So in the end, okay, one have to do the calculation with a different model to get an idea.
Yeah, sure. Well, thank you very much.
Thank you.
Okay, and next, Laura.
Isaac, thank you for the presentation. Sorry, I could not listen to the first slides. Maybe you mentioned it. I have a question. You use N-megan potentials. Why don't you use the chiral potentials?
Because I don't have them. That is the main reason. And to the best of my knowledge, well, I don't have them.
You don't have access. Okay, because I thought you had some papers.
Yeah, but I have a question, but maybe I'm completely ignorant. I don't know if these chiral models have the hyperon sector included. This is a question. I don't know. Because in particular, we needed the hyperon, and I know at least that 9 megan ones.
Yes.
Okay, also the extended ones and the 9 megan 97 they have it. But the simple answer is simply I don't have the routines.
Okay, no, because I thought since you have some papers on chiral models and equation of state, I was wondering whether you don't use them. And a second question, you don't talk about bulk viscosity. Why is so? I'm just wondering. I missed the first slide, so I don't know.
Well, because bulk viscosity is not coming from transport, from scattering. Right.
Well, it's related with expansion and or contraction, okay, in the volume. So it could be from scattering, yes. Okay, we can talk about that, don't worry.
It's okay. And just last question.
Yeah, okay, very short question maybe. Just probably, Isaac, I think that the temperatures are too small for you to consider the a temperature dependence of the G matrix, right? Because you know how to do that.
Yes, yes.
Okay.
Yeah. So the calculation, let's say, is enough. The G matrix are calculated at 0 temperature, but this is not changing absolutely anything, because if you go, so see, the largest temperature is 10 to the 9 Kelvin, which is
0.1 MeV or something like that. Okay.
Small, so this is not going to change anything.
Okay. Thank you very much. Thank you. Right. Great.
Okay, so thank you, Isaac. And let's move on to the final speaker in this session. Okay, Laura, can you share the screen?
Let's share. Okay, and now I have to make it full screen.
Okay, and next speaker is Laura Torres, and she will give a talk about strange meson in a nuclear and neutron stars. So Laura, is it okay? Full screen, it's okay.
Yes,
please.
it's okay now. Okay, great. So thank you very much for the invitation. So now I'm moving actually to mesons. So I wanted to talk about part of a discussion we had on a review we recently wrote with Laura Fabietti on kaon physics. And basically, I would like, to show a bit of what has been done. And I'm sure, I can see a lot of the participants in the meeting have been working on that. So if I report something that they don't agree, please jump at it. So I just wanted, to give you an overview of the field in the past years and, well, in the past maybe decades already. So I will, let's see if I can. So the outline of the talk is going to be about anti-kaons. Basically, I will also mention a bit of kaons. So you can see here, I'm going to discuss a few ideas about the anti-kaon nuclear interaction and the lambda 1405. I think already in the first day, there was something on that, in particular on the anti-kaon nucleon bound state. And then I will move actually to matter. So I will show you a bit what has been done for kaons and anti-kaons in matter. And then after, having this theoretical framework and discussing about a bit of theory, which I'm going to do here, I will just jump to the experiments and observations. So basically, I will discuss a bit of kaonic atoms, also heavy ion collisions, and finally neutron stars. So this is a slide, kind of summarizing a lot of work over the last decades, in the sense of this famous lambda 1405, right? That we already, most of us know, it comes in the isospin 0 channel, and this scattering anti-kaon nucleon is governed basically by the presence of this lambda 1405, which is lying, like around 30 MeV below the anti-kaon nucleon threshold. And already, the existence of that resonance already goes back to the 50s, proposed, the idea by Dalitz and Tuan. And I just wanted to point it out that since the 90s, it has been, really a revival on the scattering of anti-kaon nucleon, in particular using unitarized theories that are based on meson exchange models or Euler Lagrangians. So here I'm just giving you probably a not complete list of works doing anti-kaon nucleon interaction using meson exchange models. Basically these are on the Jülich meson exchange model. And then moving, in the Jülich meson exchange model, and more, precisely since the 90s, since the chiral Lagrangians, the effective field theories. So we have lots of work in that direction that has been, with time improving on, going beyond Weinberg-Tomaszova interaction, including, lex to leading order or Born terms, which come into the S channel or the U channel, and of course, including fits to new data that has been appearing over the years. So just as an example, I just wanted to show you, this famous 1s state of the kaonic hydrogen that, Siddhartha collaboration, has determined, the most precise value of the shift and width of this state, basically helping, to resolve the issue of the discrepancies between Keck and Deer. So here I took it actually from Albert Feijó, the width and the shift of this state, and you can see here the Keck data and the Deer data, and what Siddhartha is lying, so more into the direction, of Keck data. And of course, here you have several theoretical groups, giving you some information or giving you what the model or the scheme is giving on this one is state. How did they do that? Just an example of one of them, which is the Ikeda-Hyodo-Weise results, like going through, this desert type formula where you have the shift and the width correlated, with the scattering lengths. You can see here that using this information, for example, in this scheme, this is a chiral scheme, up to next to leading order, what they have, done, using this information on the 1s state, just to have the best fit using this next to leading order, and getting information on what is subthreshold. Okay, so getting, how the scattering amplitude, the real and imaginary part looked like, using this next to leading order fit, using this one as state of the kaonic hydrogen. Of course, there has been several other groups, and the nice thing, at least from us, for our theory, is that we have these data results, which of course provide us important constraint on our theoretical descriptions. Also, another, about the lambda 1405 and the double pole structure of the lambda 1405. I think more or less the community agrees, that we have like the lambda 1405 as a superposition of two poles with different couplings to the pi sigma and antichaon nucleon state. So here I show you, taken from the PDG, actually different groups and the different determinations of this two-pole structure. And here, just showing you the measured spectra of the sigma pion final state associated, with the lambda 1405. For different reactions, we have here the kaon-induced reactions, which is the red one. And then we have also the pion-induced reaction, which is the blue one here. And as you can see, the kaon-induced reaction actually, shows you, or let's say it's more biased, let's say, by the presence of the high energy pole. This is because basically, we have, once one of the pion is emitted, we have the antichaon nucleon interaction going to antichaon nucleon going to pion sigma, which is dominated, this interaction, by the presence of this high energy pole. On the other hand, as you can see, for the pion induced reaction, we have actually that the dominant contribution is coming, from this low energy pole. I'm also showing you, briefly the progress in lambda 1405 production. So here I'm just showing you different, or pointing you to different reactions in order to produce this lambda 1405. So we have like photon-induced reactions. Basically, those are sensitive to this high energy pole. So we have reactions that, have been produced in class experiment. And then we have, reactions of the type, the photon going to a proton and then generating this lambda 1405 and a kaon, and this finally being seen in this pion sigma invariant mass. So here you have an example of the pion sigma or the sigma pion invariant mass for different photon energies. I mean, you can see these different ones. And of course, with the different decomposition in the different physical states. So pi 0, sigma 0 in red, pi minus, sigma plus in blue, pi plus, sigma minus in green. And as I said, I mean, these kind of reactions turn to be quite sensitive to this high energy pole. Of course, the theory goes over, like more than 20 years with different groups really trying to model, first the photo emission, the photo production, and then of course, then linking it, to the second part, which will be this antichaon nucleon scattering with coupled channels. Of course, as I mentioned before, we have also kaon-induced reactions sensitive to the high energy pole, or pion-induced reactions, which are sensitive to the low energy pole. And it would say more recently, due to the new experiments, so we have kaon-induced reactions in deuteron, this kind of reactions shown here, antichaon to a deuteron going to a pion sigma neutron, for example, or, proton-proton collisions like Anke, like having proton-proton going to, for example, proton, kaon, and lambda 1405. This is regarding the, as I said, you know, the anti-kaon nuclear interaction and the role of the lambda 1405. And of course, we have this famous anti-kaon nucleon bound state. Already, I believe, discussed the first day. So basically, we have here that, you know, as this interaction, this presence of this bound state, this lambda 1405, tell us, you know, that we have an attraction here in the anti-kaon nuclear interaction. And of course, the question is whether we can have, you know, anti-kaon nuclear clusters. And this actually was triggered, you know, by initial claims, of course, on Finuda, Disto, and Obelix, and has been thoroughly addressed theoretically within different models, incorporating different absorption channels, different coupled channels, different, going beyond, you know, Weinberg Tomozawa, going beyond to going to next to leading order calculations. And as I said, I mean, initial claims done, you know, by these collaborations, Finuda, Disto, Obelix, could be explained not through this anti-kaon nucleon bound state, but through other conventional explanations, or not even being reproduced, you know, for example, in Hades. There has been, of course, more recent measurements in JPark, for example, on in LEPS, which did not find this bound state, or if they have been found, for example, in these papers of JPark in 2015 and 2016, may have other interpretations, like, for example, sigma star nucleon bound states. Let's say more recently, let's say in the 2016, JPark found this structure, and actually this has been also interpreted as a bound state in this later work of the 2016. So here I just summarize, you know, maybe this is old as compared probably with the first talk that I could not attend on Monday, but just to show you, you know, where the results of the experiments are in that let's say high binding energy, and also, for example, for this JPark large widths. And here it would be, for example, this taken from this paper last year, the A15 experiment at JPark, also having, you know, large widths and, let's say, smaller binding energy as compared, for example, to the JPark A27. And of course, this data is just, this is not data, it's just theory, okay? These results from different experiments, from phenomenological experiments to chiral approaches. Now I'm showing you in this next slide kind of a summary of the different chiral and phenomenological calculation that has been used, you know, to calculate this binding energy and width of the anti-kaon proton-proton bound state. And actually, using these different chiral phenomenological calculations, there has been employed different methods, okay, in order to calculate these three-body problems. So we have variational Fadayev calculations, or more recent, which is complex, now I forgot the name, but just these CCSM methods, coupled channel complex methods, sorry. And you can see the variety of values from the binding energy and the width. And those actually, going through all these papers, you can see that the binding energies range from 10 to 100 MeV, while decay width goes maybe between 10, 15 MeV to up to 100 MeVs. So why are these different results? So basically, there is, on the one hand, uncertainties on the subthreshold extrapolation of the anti-kaon nucleon interaction. You can see that the chiral interactions give lower binding energy than the phenomenological ones. This is due to the fact the anti-kaon nucleon interaction is less attractive in this chiral schemes than in the phenomenological ones, so it gives less attraction. And on the other hand, this is not only due to the anti-kaon nucleon interaction, but also the method use. Because, you know, depending, you know, you use variational or Fadayev calculations or this complex coupled channel complex method, they has introduced certain approximations, like the fact that in variational methods, the full free body is not a count, where in FADEF calculations, they are using separable two-body interactions. And in the second one, in this complex, couple channel complex method, there is, you know, it combines the merits of both FADEF and variational, but really it's at the cost of a high computational, you know, cost. This is just regarding the antichaon nucleon and the three-body antichaon nucleon bound state. But I would like to talk to you now about matter, so antichaons and chaons in matter. So here I will start with the chaons. So for the chaons, we have, if we, assuming there are no pentaquarks, we know that, you know, we can then describe the chaon-nucleon interaction by what is called the low density theorem or the T-row approximation. So basically it's a good approximation just to concentrate on the scattering amplitude in free space and then just convolute it with density. So we have different methods over the years based on Nambu-Gianalistino models, relativistic mean field models, quark meson coupling models, or if you want more in the 90s already, unitarized coupled channel approaches using chiral Lagrangians, which gives you already a repulsion. The value, it depends a bit, but it's just around, you know, 20, 30 MeV repulsion at saturation density. Regarding the antichaon nuclear interaction, this is more complicated because of the presence of this lambda 1405. So actually, there are, again, calculations in relativistic mean field or quark meson coupling models. And as you can see here, kind of for the antichaon nucleon, this is an old paper. I mean, there has been more works on that. I just actually took one of the first ones just to show you this shift, this attraction with density, which is kind of important in this approach on relativistic mean field. We also have phenomenological models. So we have density dependent potentials, for example, fitted, you know, in this case for kaonic atoms, which also give us an important attraction. And just to mention that more recently, there has been, you know, in this direction, using antichaon nucleon scattering amplitudes, using chiral models, chiral effective field theory, which has been supplemented to take into account multi-nucleon interactions, has been supplemented with phenomenologic terms, and somehow now is giving us an idea that probably these density-dependent potentials are valid just for densities not so close to saturation density. Okay. Now, from the point of view of unitarized theories, well, the idea is, of course, here I'm giving you more details, but just that you know that the idea is to solve a similar equation as we have in free space. So this scattering amplitude, only that in the medium comes through the intermediate propagators. And of course, the idea is that if you look at the meson, which are being dense in medium, you have also to solve together with this scattering in matter. We have to solve, of course, what is called Dyson-Zwinger type of equation, where you calculate the self-energy. So the interaction of each of these particles, the chaons, antichaons, with the medium. So this has to be solved says consistently, and at the end of the day, actually, these are the main ingredients that come into this many-body calculation. So we have Pauli blocking, we have the self-consistent calculation of the chaon dressing, and of course, also the inclusion of pion dressing, which also becomes important because of the important chains of pions in the medium. So once you do this calculation, what you get is this spectral function, which at the end of the day is kind of a, you know, it tells you like the probability, it's kind of a probability of finding this particle at a certain energy and in a certain, at a certain energy. So here we have an example of a model for different temperatures of the spectral function. And as you can see here, that these calculations are done at zero momento and also at finite momenta. And if you look, for example, at 2 times saturation density, you observe for this black line, which is the temperature zero calculation, you observe like a rich structure. So this is not a bright Wigner, this is something more complicated because of the presence of all these particle Hall states, all these, for example, resonance Hall state, this lambda 1405, but also the presence of lambda sigma Hall state, which has the same quantum numbers of the antichaon. Why is this important to control, the spectral function in matter of these particles? Because, especially because if you move, to high energies and high momenta, there are important contributions that are not appearing, for example, for kaonic atoms, but are important for heavy ions. And now I'm coming back. I'm not sure, maybe I have like 5 minutes more to tell you a bit about, how observations and experiments compare with all these theoretical approaches that I mentioned. So I will first talk about a bit kaonic atoms. Okay, we have these kaonic atoms where are atoms in which an electron is replaced by a negatively charged antichaon. So the idea, of course, is you use, for example, a phenomenological model and coming, from best fits of kaonic atoms, and this gives you an idea that of what is the potential, the attraction that an antichaon feels in the medium. So those best fits to kaonic atoms seem to prefer using these phenomenological approaches, an attraction of around -200 MeV at saturation density. But then you move, to chiral models, and albeit using some additional moderate phenomenological piece, even having not so large attraction, okay, it's like -50, -70 MeVs of attraction at saturation density, you still get good reproduction of the kaonic atoms. So this is probably telling us that this attraction at saturation density is not well described, or is not accessible through kaonic atoms. And actually, this is kind of the conclusions, on these papers, in the sense that they try different, let's say, models. They use, for example, if you look here, this is single nucleon absorption fractions. So here you have the experimental data, the band, okay, coming from bubble chamber experiments. And if you see here, using two different chiral motivated models. This is the Prague the Prague model, and this is the Kyoto Munich model. And you can see that both of them, give reasonable results for these absorption, single nucleon absorption fractions. These are for the upper states, and these are for the lower states. And then if you look at really the real and imaginary potential, you see the divergence, of these models. For example, this would be the phenomenological model, and this would be one of the ones that is used here, the Kyoto Munich. And you can see that depending on this alpha value, which is telling about this phenomenological term that takes into account multinucleon interactions, you can see here that both of them more or less agree, at lower densities, not only for the real part, but also for the imaginary part. So somehow already it's telling us that kaonic data is reproduced, but kaonic data does not constrain the optical potential for densities around saturation density, but, lower densities. Just a few words on heavy ion collisions. So there is also a lot of interest in STRANGENess production, on kaon production. So we have experiments on low energy, high energy heavy ion collisions, on high energy heavy ion collisions. And as you can see here, I just put you some references of the different experiments and what they have been looking. So they have been looking this, for example, low energy, high energy collisions to kaons or phis, or also vector like K star. High energy as well, they are looking, to K stars, phis, and also baryons. And of course, there is more progress being done, or already starting, but, the future going through CBM at FAIR, or NICA, or RIC, or also JPark and heavy ion program. And some of the conclusions here, for example, on using information on the low energy heavy ion collisions. So we have chaos results, for example, from the chaos collaboration. So we have like kaon telling us that it's a proof for an equation of state, because they are created in the initial state and then propagate without almost interacting with the medium. And the fact, for example, that kaons and K minuses are correlated because of the production of these particles, like kaons being produced in the primary collisions, and in these primary collisions also hyperons being produced in such a way that then kaons can be produced in these strangeness exchange reactions. Of course, because of the different mean free path, basically of the interaction, we have different freeze out conditions for the kaons and K minuses. And the idea that they are pointing is that they are observing kind of a repulsion for kaons, while the attraction as for an attraction for the K minuses. There is also the discussion there about the role of the phi and whether this is masking somehow the interaction, the information of the K minuses. So, and this is actually something that was pointed out already by the community in like a few years ago. And more recently, there has been development on the kaon and anti-kaon production on heavy ion collisions, and the fact that, you know, the comparison of the theory with the data of chaosphopy and others experimental data, and the fact that they observe a different behavior of the kaons and the K minuses, basically motivated by the different interaction with the medium. So just an example, the kaon production compared to the anti-kaon production, the fact that we have a repulsion of the kaons as, in the medium, it tells us that it's suppressing the production, whether the anti-kaons, the production of anti-kaons is enhanced due to basically the broadening of this spectral function, because of not as much because of the attraction, but just because of the broadening. And of course, this different behavior of kaons and anti-kaons in medium has differences on the spectrum of kaons and anti-kaons, and also what is called the elliptic flow and the direct flow. As well, the kaons has helped somehow to give us an information on the equation of state of the medium that is creating in these heavy ion collisions. And then just finally, a couple of words, you know, on kaon condensation. So this actually was brought already in the 80s about the fact that if the kaons have or feel a strong attractive interaction with the medium, this might lead to condensation of kaons in neutron stars. The fact that kaons could appear in these neutron stars and then lead to of course, as being bosons, to condensate in neutron stars. So people usually look at the reactions that might happen inside neutron stars, this kind of beta equilibrated reactions where are explained, or, you know, you can understand in terms of the chemical potentials. So basically the idea would be that in order to have kaons, basically the chemical potential of the electron has to be larger than the chemical potential of the anti-kaons starting to some certain density. So somehow the idea would be is the mass of the anti-kaons is modified in such a way that it's smaller than the chemical potential of the electrons, then kaons will appear. Well, just a few words, just telling you that, of course, this would imply modifications of the mass of around 200, 300 MeV. That, as we were discussing, for the unitarized schemes, this doesn't seem to be the case. So within these models, let's say these models based on chiral unitarized model or meson exchange models, this seems very unlikely. So just my last slide, just that I wanted to show you a bit what has been done in the field over the past years, you know, kind of a small summary on anti-kaon nuclear interaction and the role of the lambda 1405. And of course, the idea that the interest has been focused on unveiling the nature of this lambda 1405, and especially over the past years on these anti-kaon nucleon bound states. And the fact as well that kaons in matter and anti-kaons in matter are also being investigated, correlated, not only with kaonic atoms, but also with heavy ion collisions, and of course, also in neutron stars with the phenomena of kaon condensation. So thank you very much for your attention.
Thank you very much. It's a very nice talk. Laura, and then now paper is open discussion. Okay, do you have any question or comment? Okay, all of you.
Me, I was, okay, thank you very much. Laura, I mean, that was an impressive talk. I can also see that you have been working on this review with Laura Fabietti.
Yes.
Okay, very nice. So let me ask, I mean, more than questions, just a couple of comments. I mean, I have not been following, details lately, but I'm gladly, surprised, to see that people, different groups, lately have converged to the thing that it looked, quite obvious from the beginning, that kaon atoms don't give information on the self-energy of the kaon at densities like ρ0, but much smaller. Sometimes that was a hot topic, and there were heated discussions on that. And I'm glad, the different groups have converged into the thing, which is that you cannot extrapolate from kaon atoms to ρ equal ρ0. Good. That is nice. I think, everyone has collaborated to that, so congratulations to all. So now I wanted to make a comment on this table that you put there on the K bar NN.
Yes, I can share it again.
Yeah, there is indeed, a very much a big dispersion of data.
Yes.
But as you mentioned, that area, as you mentioned, the chiral models always give, smaller binding.
Yes.
But I wanted to make a comment there. That for example, with that Ikeda and Sato. You have two results there, right?
Yes.
One is around 916, the other one is 1695. Yeah, I think the difference, the more recent is the one of 916. I think the difference is that in one of them they use, a energy independent potential, which is the one that gives very large binding. And in the other one, they took, energy dependent potential more in the line of the chiral theorist. And that's the one that gives them, the 916. Okay.
Yes.
So I think we are also converging, to moderate, values there. And fine, I don't want to comment on those of Yamazaki, we all know. But in the last comment, is about this table at the beginning that you have borrowed from Nagai.
This one, yes.
This one, yeah. I know what happens, is one produces a picture and then it goes on forever. Everyone copies. So since Nagai is there in the audience, I would ask, him to retouch it a little bit, very little, to remove, don't remove the others. They have been disputed and all that and given alternative explanation, but this two should disappear from there. These two should not be there, should have never been there. Is that this never, the slightest, thing, to discuss about the signal. And I say that because you, and I have read your report with Laura, all of it. And I see that one of the things that you discuss in the report is that this two is, not a signal at all. That that the normal, consideration, of the reaction that you have there, in phase space, and the cuts that these fellows put, they give exactly, the signal that they observe. So that was never, that was never, it's a, a signal, of a bound state. I think, this should disappear from there. And Nagai, at the same time, since you remove that, you can add another one. You can add the one of Bayar, Bayar. On the theory, you put Bayar. Bayar is as serious as all the others, so you can put there Bayar.
Yeah,
okay?
May I comment, Eulogio? For example, I also took, he's also, author, I think Nagai, if you want to answer, Professor Nagai, I believe, I don't know exactly, I have to look it up, but I also hear the different chiral models. So maybe we have to look at those more recent plot and see what are the different models that are being used here. Okay?
Yeah, at some point, this plot was produced. So that it doesn't care about the most recent one. I'm sorry.
Well, it's okay. You always can. Slightly change that. It doesn't take you much, and everyone will be happy.
Yeah.
Okay,
This is a one shot in some time.
Very good.
Okay, so any other question? Okay, Albert, so you still have some question or not?
No, sorry, it was a mistake. It was by mistake. Sorry.
Yeah, that's all. Okay, so thank you, Laura. And so let's finish this morning session. Okay, thank you.